to the cloud. That's out of the way right now. And yeah, like I said, we're gonna tackle this problem again. This time we'll start off with the numWorks calculator. All right. So the question, the problem, the concern was to use the empirical rule to determine whether the following data follow a normal distribution. It feels like a typo. Follows. Anyway, I'll let you be the judge of that because obviously grammar is not my strong point. So what we're going to do if we're using numWorks, all right? So this screen is I'm using the app, so it's a little nicer, but we're gonna it's touchscreen. So I'm going to go into statistics. So I hit the home button. So I'll just jot it down here for numWorks. You're going to hit home. I can't draw the picture of the house, so I'm just writing home. Statistics. All right. So I can hit OK or enter on statistics. And it brings me to my data editor. Now, this is information I had from another class. So you're going to run into that scenario. Anytime you use a calculator, if you use it for something else before that, you might have information that's in the way. All right. So to clear the list, we go. So I'll say to clear the list, go to value V1 and hit enter and hit OK or enter. I'll make this look more like a 1. Value V1 and hit OK. All right. So right onto the red and hit OK. And you'll see an option that says clear table V1N1. That's what we want. So we go to clear table. All right, and I'll explain what the N1 part of it means in a second. But in this list, you can see that it also gives you an option to display a column for cumulative frequencies if that ends up being an issue. Right, but I just want to clear this table. It'll ask me, do I really want to do it? Some other calculators don't do that, and you're searching for the undo button. This one's asking you, do you really want to delete the stuff that's in the list? Yes, I do. So it's gone. All right, now I'm just going to type in my values. You start off with the X list. So 14, 16, 18, 20, 22, and 24. All right. And you'll notice that it automatically puts frequency values of 1 in for each of these numbers because it assumes that you only want that number to show up once. But I don't actually want it to only show up once. I want it to show up more than once. So, well, the first one I want to show up once. The second one, I want to show up 7 times. So that 16 occurs 7 times. 18 occurs 14 times. 20 occurs 13 times. 22 occurs 5 times. And 24 only occurs once. All right, so I can leave that one alone. All right, so I have my data in. If you remember from last class, I know it was a week ago, so maybe not, we're really looking for 2 pieces of information. We're looking for the mean, so the sample mean, which is X bar, and the sample standard deviation, which is S. All right, so to get these values, so these 2 values, we go to stats. All right, so we go right up the line here until we're in the column heading areas and go right to stats and then hit OK or enter. And we have a ton of information. They give you everything. They give you everything that they think is relevant. All right. But we want to go down the line until we find the one that says sample mean, which is 18.82927. But if we're rounding to 3 significant digits, it's 18.829. And the sample standard deviation S, 2.144 if we're rounding to 3 significant digits. All right, so that's the sample mean and sample standard deviation. Now, I'll show you in a couple of minutes how to do it on Desmos, but for now, I'm just going to say that's all we need really any kind of special type of calculator for. Everything else is just rote number crunching. All right, so I'm going to compute based off of this rule here, X bar plus or minus 1 standard deviation. And so the way that is, I'll leave it over here for now. X bar minus 1 times the standard deviation, and X bar plus 1 times the standard deviation. All right, that's our first computation. Then once we've completed that computation, we're going to do, if necessary, we're going to do it 2 more times, but this time with 2 times the square root of nothing, 2 times s. And then 3 times s. All right, so those are our 3 sets of computations. Now, the issue that we run into is that that's a lot of typing if you don't use technology to its fullest advantage. So I'm going to go back into my home screen. All right, so I'm going to hit that home icon. If you're ever in doubt and you're like, where should I go from here? Odds are you're going to go home and just kind of recalibrate. Well, what do we want to do? We want to make some calculations. So I go into the calculation menu, hit OK. I have other stuff from another class here, but I can start doing my computations because I know what X bar is. And I know what S is. So everywhere in these formulas that I have an X bar, I'm going to replace it with 18.829. And everywhere I have an S, I'm going to replace it with a 2.144. You don't actually have to show the substitution. That's just writing for the sake of writing. You could just go right to the bounds. All right. So what I mean by that is I'm going to run this computation here. Let me make that look a little nicer. This computation here, then this computation, this one, this one, this one, this one, and put our results right below it. All right. So X bar, which is 18.829, minus 1s. So 1 times s. So 1 times 2.144. All right. That's going to be my first computation, which gives me a 16.685. All right, so that result goes right here. Then I move on to the next computation where I take it's the same X bar and the same S, except now I'm gonna be adding instead of subtracting. So I'll hit my up arrow and I'm gonna recall this previous computation. Once I highlight the thing that I want, I mean, if I wanted this one, I'd go up there. If I want that, I'll go there. You just toggle back and forth until you get what you're looking for, and then hit either OK or Enter. It brings it, OK or Execute. It brings you to the bottom of the screen where you can make edits. All right, so I'm going to go over here and change that minus to a plus. All right, and then I'm going to hit Execute or OK. And I'm going to get 20.973. Oops, 20.973. For the sake of learning the skill, I'm not going to account for any percentages yet. I'm just going to go right across the line here and just keep running computations. So up arrow, go back to the one that has a minus. I need this, really this structure, but that one needs to be a 2. All right, so X bar minus 2 times the standard deviation. So my low bound is going to be 14.541. Just go up, change the minus to a plus. And I get my upper bound, 23.117. Right? So all I'm doing is changing ones to twos to threes. Now we're doing the threes. So I grab the one with the minus, change the 2 to a 3. Oops, that's not a 3. And I get 12.397. My upper bound I'll get by changing that minus to a plus. 25.261. All right. So these are the three regions of interest. The first one gives us 1 standard deviation away from the mean. The second gives us 2 standard deviations away from the mean. And the third gives us 3 standard deviations away from the mean. Right. So what I want to do, just looking at this column here, the X values, I just want to take note of which ones fall between these two numbers. All right. So in this case, just get rid of that for a sec. I can tell you that 14 is not big enough. It's got to be between 16.685 and 20 point. Well, I'll just say 16.7-ish and 20.9-ish. All right. 14 is not there. 16 doesn't quite make it. 18 falls between those two numbers. 20 does, barely, but it does. 22 does not. Neither does 24. So the only two numbers that are relevant here would be 18 and 20, but we have to remind ourselves that the 18 occurs 14 times and the 20 occurs 13 times. All right, so that's a total of 27 values. There's a total of 41 values in the entire data set. We get that by adding these numbers up. So 1 plus 7 is 8, plus 14 is 22, plus 13 is 35, plus 5 is 40, plus 1 is 41. All right, so a total of 41 values in the data set. All right, that's just adding them up. So I'd want to see about what percentage this is. All right, so 27 divided by 41 is in the neighborhood of 66%. It's just a smidge short, but if I wanted to put this as a percentage, I would say about 66%, but this number corresponds to point, if we're rounding appropriately, 658, which in turn is about 66% if we're going to the nearest whole number. But if we're not going to the nearest whole number, then we would leave it at 65.8%. And you'd say, well, it's not quite close enough, because we defined approximately to be about 2 percentage points. All right. So it's right on the border. Right? It's close to 68%. We want it to be 68%. It's close, but it's not quite there. Right. So we'll let the rest of the data kind of decide for us. I'm sorry, the rest of the computations decide for us whether the data set follows a normal distribution. All right. So looking at the second interval of values. So we know that the first interval contains the 18 and the 20. 14 is still too small, right? This goes from about 14 and a half to a little bit more than 23. 14 is too small. 16 is fine now. 18 is good. 20 is good. 22 is good, but now 24, well, not now, but 24 still doesn't fall in the interval. All right. So my second set of computations gives us this region. All right. The numbers 16, 18, 20, and 22. right? But really we're focused on how many each number occur, or how many times each number occurs. Here I can say that, well, it's 12 more times than the previous interval, because I now have a +7 and a +5, right? So that gets me up to 39. Yeah, 39. So 39 out of 41.
I have a question. Where did you get the 41?
The 41 is the total of the values in the set, if you add up the frequency column. All right, so we're looking at 0.951, all right, which does round to 95%. All right, so what we're looking at here is something that was kind of on the borderline for the first interval, but for the second interval, it's right at the target number, the 95%. Right, so now we're just going to investigate the last case, which is going from about 12.4 to about 25.3. Right, every one of the values falls in that interval. Right, every one of these numbers here, let me just do this real quick and then zoom back out. Every one of them falls in the interval. So if I account for every one of the values, there are 41 values overall, but all 41 of them fall in this interval. All right, and again, just by taking the numbers, I'll just do it on the screen here. 1 + 7 + 14. I missed the 7 + 14 + 13 + 5 + 1, total of 41 values. I'll show you another way you can get that in a minute, but this would give us, well, there's no need to go to decimal form here because it's going to give us an even 100%, which is definitely within 2 percentage points of 99.7. All right, so we actually never say something is a normal distribution. We say that it follows a normal distribution. All right, so it has this same structure and roughly the same percentage values as a normal distribution, but it does not ever have to be exact. So what I would say as a conclusion here, which is the opposite of the conclusion when I had that snafu last time, is the data follows a normal distribution. All right. But again, you might put a little asterisk on this one here because it rounded to 66%. It was pretty close. Another person could come along and say, well, it's not by the book. It's not exactly 2 percentage points away from 68%, so it's out. But we do allow for gray area, right? So it's very, very close. So we're going to let it slide, basically. And just think about it like if you put an answer to a question on a test and maybe you didn't get the notation exactly 100% correct, but I could look at it and say, oh, but you're so close. I'm going to let it slide. I'll give you full credit, right? It's along those lines.
I have a question.
Yes.
Hi. So the first one, are you big on the approximation sign, especially when you're dealing with the decimals?
It's not really necessary. I mean, if it occurs to you to put it in, but I'm not going to be looking to take off credit if it's not there.
Oh, thank you. And the next question is, based on the data set for the middle and the last one, which is like 95% and 100%, is it because both of those fall within like higher than 95% or 95% and over 100%? Does that mean that it follows the data set?
Yeah, so because it's right at 95% and it's so very close to 99.7%, we would say the first category is pretty close, the second category is spot on, and the last category is very, very close. So if you can meet those 3 criteria, then you would say the data follows a normal distribution.
Thank you.
No problem. All right. So just very quickly, let me bring up Desmos here. That's not Desmos. Actually, I don't even remember doing that. So let me go to Desmos, learn together. And the calculator that we used was measures of center and spread. All right, so this one, again, it was for a single list of data for a frequency distribution. Really, the only thing we need a calculator for, a special kind of calculator, like I said before, is for the mean and standard deviation. All right, so in the Desmos calculator, I type in my X values, just like I did in the NumWorks, 14, 16, 18, 20. Oh, it assumed what I wanted, so I should have just let it go. And then my frequency values 1, 7, 14, 13, 5, and 1. All right. So this is not a single list of data. It's a frequency distribution. So I'd hit the little drop down there. It'd give me the sample mean of 18.829. And it'll give me the sample standard deviation of 2.1. Well, it should be 4.4. So even this is not working. Oh, wait, no. You know what? Welcome to the world of me. I don't think I'll ever create something in which there isn't a typo. So the Desmos calculator that's stored on Brightspace, I have to make one final adjustment. It should be -1 on the bottom, but it will give you the 1.44. I'm sorry, 2.144 when I'm done whipping it into shape, because it needs a little bit more tweaking. But really, this is all you need. And then from there, you do the number crunching just the way we did here. You take your numbers, 18.829 minus, I'm not going to do each one of them again, but I'll just do one of them just so you see, 2.144, and you'll get your 16.685. Now, the thing about Desmos that's a little bit different, I mean, it's different from everything else, but noticeably different, is that, I mean, you could use a mouse or a trackpad and copy paste from one field to another, or you could hit that little gear icon and that double piece of paper icon there, just tap on that, it'll duplicate, and you could just make a quick adjustment. All right. So, you know, there's pros and cons either way. You know, in the end, I wouldn't begrudge you if you said, you know what, I'll just use both of them. You know, I'll use NumWorks for this and I'll use Desmos for that. You know, I leave that part of things up to you. All right. But the next example talks about really the same thing, but now it gives you a little bit of context. Data below is a distribution of the ratings of teaching effectiveness for the students in a large introduction to psychology class. There are 400 students in the class. The questionnaire provides students with 15 statements, and the student is asked to pick a number between 1 and 5 that indicates the degree to which they agree or disagree with each statement. One of these statements is the instructor in the class or course is outstanding. A response of 5 indicates that they agree with it fully, and a response of 0 means that the student disagrees with the statement completely. Personally, I think 0 should be disagrees completely, but you know, it wasn't my study. All right. So we want to visually determine whether the following is a normal distribution. All right. So looking at the previous example, a normal distribution, first and foremost, needs to be symmetric. All right. It doesn't have to be exactly symmetric. It should be roughly symmetric, with the smallest frequency values associated with the most extreme X value. So the smallest X value should have the smallest frequency value. The largest X value should also have one of those smaller frequency values. All right. If it's not symmetric, I would not think that it's a normal distribution. All right. And so what we're looking at here, and first off, the X values are in reverse order. So kind of like a little trick question here, but the calculators aren't going to fall for it. So it's fine. All right. But they are in order. And I'm looking at, in the top value here, I have a 150, bottom value, I have a 5. That doesn't seem very symmetric. These two numbers should be in the same neighborhood. These two numbers should be in the same neighborhood. All right. If they're not, it's probably not a normal distribution. All right. But it is possible that they jumble up the X values so crazily that you don't realize, oh, it is symmetric. It's just if I put it in order, I'd see that. All right. So let me go to NumWorks. Let me go to NumWorks. There we go. We're gonna go home. So it's the same process. All right. So that's the good news. Bad news is it's still kind of a process. So, okay, on calculate. Oh wait, no, we're not there yet. What am I doing? Statistics. We want to put fresh new data in here. Now you can overwrite data values. So I'm going to hit okay on data. I can overwrite these values and delete what I don't want, or I could just wipe it all out in one shot. There's pros and cons either way, but the most notable pro to not wiping it out is if the data you're typing in is just a minor adjustment from a previous data set, you might just want to overwrite some of the values, not all of them. All right. But this is completely different. So I'm going to go right up to V1, hit OK, and clear the table. It'll say confirm, I confirm, and now we have a blank slate. All right. Alternatively, I mean, I suppose you could just reset the whole calculator, but the thing is, that really only works with handhelds. All right. So handhelds you got to pay for. These are free. We're just going to be overwriting values or deleting them as we go. All right. So I'm going to type in 5, 4, 3, 2, 1. And then again, like I said before, it auto populates the frequency values. Instead of 1 all the way down, I want 150, not 150, 150, 200, 40, and a couple of 5s. All right. So my data's in. I always do a quick double check just to make sure. I mean, there's no reason why you wouldn't want to double check your information. I mean, as we go forward, we're going to find that really the only way we can screw some of these things up would be by typing the data in incorrectly. So we just want to be careful about that. Right. But once you have it in, you go to stats. Now you could make a graph. I mean, if you're not really sure about the information, you know, like, is it symmetric? I don't really know. Then you could take a look at the picture, right? It just depends on what picture you want to look at. I recommend a box plot, all right? So you would be able to see symmetry in a box plot if it existed, all right? Without even really getting into too much about how to construct the box plot, because that's, you know, not even necessary because the calculator is going to do it. You can take a quick look. Oh, I got to actually be on graph and go to the one that says box plot, and it'll make a box plot. And you just look at it and say, does that look symmetrical? I did alter one setting for another class. Let me just go back. I'll go to the default setting. This is what, as a default setting, it should look like. All right. Or look, I mean, comparing it to an ordinary box plot, a box plot should look like, and I'll just jot it down up here. There's a whole page later on in the packet that talks about types of graphs and how to interpret them. But just to give you the gist, an ordinary box plot would look something like this. This would be, I'm sorry, a symmetrical box plot. You'd have the box in the middle, the tail's going out, the tail's roughly the same length. They don't have to be exactly the same length. But that's what a symmetrical box plot looks like. This does not look like that. All right. This actually looks like what a box plot would be if this were all the way over here. You know, actually I grabbed onto too much here. If this were like over here, it's lopsided. That's not symmetrical. All right. So you can get a look at the box plot and that'll tell you or give you a sense of the symmetry, but I want to apply the empirical rule. Right. And when I say visually, there's nothing about that that says you must create a graph. I mean, if you could look at the raw data and see that it's not symmetric, then that's good enough. All right. But if I go down the line here to sample mean, which is 4.213. So X bar 4.213. And the S value right below it is 0.771. And that's one of the things about the online version of it, you know, like going through a web browser as opposed to the app, is that there isn't the whole like, is that a 0 or is that an 8? You know, there is an option to show the enlarged screen so you can see it pretty easily. So it's another feature I like. But we're going to run through the same computations we did before, X bar plus or minus 1S, 2S, 3S. So it doesn't really change in terms of what you do. It's just what you get and what it means. All right. And so this is how we computationally verify a normal distribution. So I'm going to go into my home screen, go to calculation, and just start crunching numbers. So again, same idea as before. We know what the S is. We know what the X bar is. It's just a matter of, you know, find and replace. So 4.213 minus 1 times the standard deviation of 0.771. So 3.442. Then again, highlight the thing and hit OK and change a minus to a plus. 4.984. Now this time, instead of going through all these other computations, because I suspect that it's not symmetric, and because if it's not symmetric, it can't be a normal distribution. All right, but just because it is symmetric doesn't mean it's a normal distribution. But if it's not symmetric, it cannot be a normal distribution. Right? It's kind of like a logical linguistic gymnastics. So I'm looking at 3.442 as the lower bound of my interval. 1 doesn't fall in that interval, neither does 2. 3 doesn't fall in that interval. Just short, but it's not there. All right. 4 does. 5 misses it by just that much, a smidge. All right. So the only value that falls in this interval here would be the number 4, and that number 4 occurs 2 times. All right. Not 2 times, 200 times. So we have 200 values that satisfy the criteria. Now, we want to sum. We want to know how many there are overall. That's what we did on a previous one. I just didn't show it. 150 plus 200 is 350. Plus 40 is 390. Plus another 5 twice is going to give you 400. Now, that being said, they did tell us that we should be on the lookout for 400 students. All right. So that's kind of noteworthy that you can actually come up with the sum just by, you know, the total number of individuals just by looking at the problem that's given, you know. So 200 out of 400, that's 50%. I mean, you could show the decimal, but it's spot on 50%. Now, the thing about that is that in order to verify a normal distribution, you need to satisfy each of the 3 criteria, this one, and this one. All right. If any one of them fails, it's not a normal distribution. All right. This is not just 2 percentage points away from 68. It's nowhere near 68. All right. So not near 68%, 68%. Therefore, 3 dots in the form of a triangle means therefore. You can write the word, You could write so, comma, or in conclusion, or however you want to write it. I just symbolic notation. It saves time and energy. All right. Therefore, data does not follow a normal distribution. All right. Data does not follow a normal distribution. All right. So that's as a student, and actually, honestly, if I'm being fair about it, as a teacher who has to grade students' work, I'm kind of rooting for this situation here. I want the case where it fails and it turns out it's not a normal distribution after like the first step. It's less for you to write and less for me to grade. All right. In this case, there's a lot more work involved, but in terms of what you gain from it, it's more statistically relevant. All right. At least as far as we're concerned. All right. So that's how we verify something's normal distribution. Now, if you know a data set is distributed normally, then we could use, I mean, there's a whole world of probability and other forms of mathematics that come into play where, and I'll say applied math, not theoretical stuff as much, but you can actually do a whole lot of math if you know a distribution is considered normal. And one of those things is computing z-scores and determining whether values are usual or unusual. But there's actually, most of our third unit in this course is going to be related to normal distributions. All right. So we're going to spend a lot of time learning the structure first in the first couple of units. But then after that, we'll put it to use and actually draw some meaningful conclusions, which is kind of cool. All right. So with that in mind, we have these lovely formulas here. Z is equal to x sub I minus x bar over s, right? Just talking about the structure of that a little bit. The x sub I represents any individual data point. All right. The x bar and the s, that's the same x bar and s that we had up here. That's talking about the mean and the standard deviation for the sample. All right. Now, these two symbols here and here stand for population mean and population standard deviation. All right, population mean, population standard deviation. We're not going to really do anything with that in this unit, but it does follow the same structure as the z-score for a sample. So it's worth bringing up now. Just know that this is more of a unit 2 thing. So this is more in unit 2. All right, so for practical purposes, we can say at this point, we don't have to worry about it right now. All right, but this other formula we do. All right, that's going to be the main component in the next example. Actually, the next 2 examples. All right, so let's dive right in. Michael and Jane are in different math classes. Michael scored a 75 on his math test. Jane scored a 73 on her math test. The mean score in Michael's class was 73, standard deviation was 7.2. In Jane's class, the mean was 71 and standard deviation was 6.3. Which of these 2 students scored better relative to their classes? Key term there, relative to their classes. I'll highlight the whole thing. All right. We already know who did better. Michael got a 75, Jane got a 73. All right. One did better than the other. But did one take a harder test? They're in different math classes. Are they even in the same unit? You know, maybe the unit was more challenging. How do we know which one showed more mastery over the content that they were learning? All right. So what we do is we compute the z-score for each one of them. Michael and Jane. We're going to find the Z in both cases. Now that Z-score, it goes back to that ruler analogy I used last class. It's really saying that we have a data set that has a mean and has a standard deviation, and we have individual scores. What we're trying to figure out is how many standard deviations each value or each relevant value in this case is away from that sample's mean. All right, that's like the kind of mind-bogglingness that statistics sometimes offers. If I tell you that the value is 3 feet, all right, but I want it measured in inches, you'd have to do a unit conversion. You'd have to say, okay, how many inches are in a foot? All right, that's 36 of those inches. All right, you go the other way and say you have a value that is 100 millimeters. All right, how many centimeters would that be? You do a unit conversion and you see that it's 10 centimeters. All right, so you can go either way with it, but the idea is that you're taking one scale and converting it to another. All right, what we're doing here is taking 2 different scales and converting them to a third scale so that they can be compared against each other. All right, by doing a unit conversion in terms of standard deviations. What standard deviation? The standard deviation. Will it always be the same? No, because it's always going to be relevant or relative to the given data set. All right, procedurally, it really is just a matter of taking Michael's score, 75, subtracting from his score the mean, and dividing by the standard deviation. Then taking Jane's score, subtracting from that score the mean in her class, 71, and dividing by the standard deviation in her class, 6.3. That's the only crunching that you have to do. Interpretation is going to be a big deal though, right? Numerators in both cases are equal to 2, all right? Which means that each one performed 2 points better than the class average. But we want to know in terms of the individual scales, is that a good thing? All right, so I compute 2 divided by 7.2, because 2 on the top, 7.2 on the bottom, 0.278. 2 on the top, 6.3 on the bottom, 0.317. All right, so I'm going to draw a picture of a normal distribution real quick. By creating z-scores, what we do is we standardize it so that the center of the normal curve is equal to 0. All right, so that's the mean. Standardizing reduces, in each case, whatever the deviation was into a standardized value per 1 unit of standard deviation. All right, so if you look at this and kind of think of it as we took this fraction and reduced it, it would become 0.278 over 1. All right, so this is the deviation from 0, and this is the standard deviation. All right, the new standard deviation. I hit delete. If I haven't said it yet, the person who created undo and redo, it should be like knighted. All right. Same idea for this one. This is the same as saying 0.317 over 1. So this is deviation from 0. And this is the new standard deviation. because we did a unit conversion. All right, so now it becomes an apples to apples comparison. Right, they're on the same scale now. One of them was on the scale of standard deviation 7.2, the other was on a scale of standard deviation 6.3. Now they're both on a scale of standard deviation of 1. All right, so if I go out 1, 2, 3 units in each direction, just like an ordinary number line, I can actually now plot these two pieces of information on the same graph. So 0.278, I mean, they're going to be really close, but 0.278, I'll put right here. We'll go with that as 0.278. And then 0.317 is just going to be a smidge to the right. A little too thick there. All right, so one of them is a little bit further to the left than the other. But now we have a basis of comparison. We can look at them together and say, all right, which one's better than the other? Now that's another conversation, because better is not only relative to the data, but it's also relative to context. All right, you just got to ask yourself, are higher numbers better on a math test, score-wise? And the answer should be yes. But then you look at it in terms of, let's say, a golf score, if you play golf. If you don't, you should know that the lower the score you get, the better you performed. All right, and that's because it took fewer strokes for you to get the ball into the hole. If it took a person 100 strokes to get the ball in the hole and it only took me 3, I'm probably a better golfer, right? So that's the idea there. You just got to look at it and say, okay, is a higher number a better score, all right? So in this case, yes. So we would say Jane performed better relative to her class. I went off the grid there. Better relative to her class. All right. You just got to be careful. I'm going to say careful, the word careful so many times that it becomes exhausting. And in fact, let's make that the word of the day, careful. Instead of kind of leaving it subtle and letting you figure it out, I'm just going to say it this time. Just say that's the word of the day, careful.
I don't remember what was last week's word of the day.
It was potato.
Oh, we didn't really say it was the word of the day.
Yeah, it was a very subtle. I was trying to.
All right.
I
missed the boat on that one.
That's all right. We'll get it. We'll get you many more opportunities before it's over. But yeah, so so just spell it out this time. Word of the day is careful. And yeah, you do have to be careful, because if you write down as a final answer here, Jane performed better. Well, no, Jane did not perform better. She got a 73, Michael got a 75. Michael performed better, but relative to her class, she performed better, right? So it's a subtle difference in verbiage, but it makes all the difference. Now, an application of this goes into what we call the usual, unusual values calculation. So we just kind of streamline that and just say unusual values, all right? Any value beyond X bar plus or minus 2S, which is the same computation that we did up here. So I can bring that right on down. This same computation will tell us whether there are any unusual values, all right? This is what we call the usual interval. All right, the usual interval, which means anything that's not in that interval would be unusual, all right? Or if your z-score is less than -2 or greater than +2, the corresponding X value is unusual. All right. If the z-score is less than -2 or greater than +2, the corresponding X value is unusual. And you could use either method where it makes sense to use that method. Right. The problem is sometimes people use one method when they should be using the other. Right. So I have two examples here for you. One of them that's tailor-made for one method and one that's tailor-made for the other. Right. And a little tip, if you see a raw set of data and they're just asking you to determine if there are any unusual values, then you're going to want to use the bracket method, this one here. Right. But I'll take you through them both. First example, given a data set in which the mean is 72 and the standard deviation is 4, is 59 unusual? All right. So we just got to be careful, because when you hear words like unusual, sometimes it makes you think that they're asking for your opinion. And they're not. They're asking for the appropriate computation. So you just got to be careful. Yeah, it seems a little out of the ordinary. I thought it looked weird. No, it's not asking for that. All right. So I have the mean 72. I have the sample standard deviation of 4, and I have an X value. So I'm going to compute Z equals X minus X bar over S, which is in turn going to give me 59 minus 72 over 4. So 59 minus 72, whoop, that's a plus. 59 minus 72, negative 13 over 4. That's going to give us a decimal. Negative 3.25. All right. And so what we get from that is that we're looking at a number that's less than -2. Oops, over shrunk it. So Z is less than negative 3.25. I'm sorry, negative 2. It is negative 3.25. Therefore, 59 is unusual. All right. Try to avoid answering a question that isn't asked. If they don't ask you in what way it's unusual, don't throw it in there, because you could make a mistake, and you never want to lose credit for something that you didn't have to put in to begin with. Yeah, 59 is unusually low, but maybe the context makes that like a better number. Maybe it's a golf score situation, so you don't want to go down that road. All right. So the Z value is less than -2. So 59, because 59 is what gave us the negative 3.25, 59 is an unusual value based off of the mean and standard deviations of 72 and 4. So you kind of look at it like, let's say a class took a test and the class average was a 72, but you got a 59, hopefully not. Right? You'd say, oh, okay, well, is that really bad? Is that bad, really bad, or terrible? Right? It's unusual on the low side, so you be the judge. If I told you that your score was unusually low, you're probably not feeling too good about that score. Right? But going the other way, unusually high, you're feeling like a champ. Because then it's like, oh, wait, I did so well that my score is considered unusual. That's how well I did. Oh, I like the sound of that. So it's a simplistic example, but that kind of hopefully gets the point across. And so the last one we'll do before we switch over to the tech assignment is number 2, obviously, because it's the last one. The following data can be considered a simple random sample of ages of NFL players as of June 2019. All right, so it's old data, but it still gets the point across. A typo, it should be determine any unusual values, not outliers. We're not doing outliers here. And then explain the meaning in the context of the situation. Don't be alarmed by context, especially if you're not familiar with NFL players, because really all it's saying is just make sure you state the meaning as best you can using the correct units. All right, these are ages of NFL players. So we'll say things like X years old, that's getting across the context, right? But the data has to get popped into the calculator. So home statistics, just going up to the data part of it, wipe out the data that we have in there. So onto value V1, hit OK, and clear the table, confirm it. The same process we've been using. All right, so again, home to get into statistics, make sure you're in data. And if there's data here, you go to value V1, hit OK, and clear that table. All right, but once it's clear and you got a fresh table ready to go, you can put the numbers in. You could type it in as raw data, or you can make it into a frequency table because some of them have repeated values, like that 27 occurs 4 times. You could do 27 in one cell and then 4 in the adjacent cell. All right, I leave that up to you. I'm just going to type it in as raw data because it's not really an overly lengthy set. Or the 34s. The 35, 36, 44, and 46. All right, I think I got them all in. Find out in a sec. I mean, just taking a quick look at the data though, before you really get started on any computation, you might say, yeah, I suspect 44 and 46 are unusual. Maybe the 22. That's the 22 seems a little low, but the 44 and the 46 seem really high in comparison to the rest of the data. All right, so you make a prediction about what you think is going to be the outcome, but then we get into the nitty gritty, or down to the nitty gritty, over to stats, and we grab the mean, sample mean. And it even has a little notation there. I mean, you really can't beat that. The sample mean is 31.25. So X bar 31.25. And S, sample standard deviation, is 6.340. All right. So I just want to do, because I don't want to go the z-score route here, because then I'd have to compute a z-score for every number that I suspect is an unusual value. I don't like the sound of that. I'd rather do X bar minus 2S, X bar plus 2S.
Why did you choose to do it with the 2S, not just because that, oh, okay, gotcha. Sorry.
No, it's all good. Yeah, sometimes it's just a rule, right? But when we get into the probability unit, we'll start to see that a lot of the rules that we learn kind of evolve from certain probability principles. This one's a little simpler in that if this interval contains 95% of the data, then anything that falls outside of that interval would have to occur less than 5% of the time. So we're basically saying that anything that occurs less than 5% of the time, we're going to say that that's unusual. All right. So, like if somebody said that there's a 5% chance of rain tomorrow, and you walked outside in the morning and it was driving rain, it was going sideways, trees leaned over and everything, like you'd be like, oh, I didn't see that coming. That's kind of unusual based off of what the report said. All right. So that's the same idea here. So we go to calculation, home calculation, and then we're just going to do the 31.25 minus 2 times 6.340. You can just put 34 if you want. So we get the low end, and then we do the high end. So again, a highlight and an overwrite. So anywhere between 18.57 and 43.93 would be considered unusual. I'm sorry, it would be considered usual. This is the usual interval. So anything that falls outside of these two numbers would be considered unusual. So if you're 18 and a half years old, it would not be unusual for you to be in the NFL. All right, oh, a little bit older than 18 and a half. But if you're 44 or 46, it would be. All right, so therefore, 44-year-old, year-old.
With the exception of Tom Brady.
With the exception of Tom Brady and I think Drew Brees.
Drew Brees, that was the other guy. That was, thank you.
No problem. So 44-year-old and 46-year-old players would be considered unusual. All right. And again, you know, context is the driving force behind a lot of things because, I mean, if like some people are really invested in the NFL, I mean, invested in more ways than one. And then there's plenty of folks that, you know, maybe have a passing interest. And some other people are like, listen, football is the round ball that's black and white and has like little pentagons and hexagons on it, and you kick it with your foot into a goal. That's football, you know. So, you know, the level of interest varies from person to person. But if you know a little bit about the sport, you probably realize that certain players, I don't know what connection was. Oh, it's the keyboard. That's fine. Certain positions can have players that really can play to an older age, and then there's certain positions where you're out of the league after 4 or 5 years because the wear and tear is too much. All right, so it could go either way, but yeah, there's no expectation that you understand that context beyond the simple context of age of NFL players. All right, so age of people. In which case you look at this and say, okay, based off the data, 44 and 46-year-old players would be considered unusual. Right, and then that's where you would leave it. Right, this isn't like a research project or anything like that. Otherwise, every problem would take us like an entire class session. All right, so we're gonna leave that there. Let me just stop this recording, and then we're gonna kick over to the tech assignment because I know we had to do a little bit more with that. Stop this recording.